Okay.
Um,
Good.
Yeah, we're live.
Hello, everyone. Welcome to Quirkcast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. A few logistical things. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode. We'll get to it. So without further ado, let's get to it. So Tim and Mikey, we were having an interesting discussion in preparation of this episode regarding the concept of like mirror universes. So I guess like kind of to start off, like why consider like a mirror? Like what's so special about a mirror, and how does a mirror like pertain to particle physics? Like, I look in the mirror, I see myself. Like, is there anything more to it?
Yeah, there's a whole lot. I mean, it's kind of bizarre, right? And like we hear the word mirror, like in Doctor Strange movie. They want to practice their magic, but they don't want to like mess up the real world. So they go into like the quote unquote mirror dimension, and it's a place where they can just play around and practice their magic, and then kind of like a training dojo, whatever. Um, And it's funny because like the idea of a mirror dimension actually has a lot of kind of like concrete merit from like real physics. And so okay, like think about when you look into a mirror, right? It seems like what you're looking at is an exact copy of yourself, right? But
Hmm.
it's not an exact copy. If I'm looking in a mirror and I like wave my right hand, the mirror version of me, if it exists, looks like it's waving its left hand, right? So it's like
Hmm.
exactly the same, but there's just some bizarro flip, right? Like left turns to right, right? So
Hmm.
it's like an exact copy, but with some weird twist, right? Um, and I guess the other relevant thing about like a mirror is that if you have two mirrors and you double reflect, you get back the original, right? So if
Hmm.
I have two mirrors set up, I look at the first reflection, and my right turns to the mirror's left, but then once it's mirrored back again, it turns back into right. So it's like left, right. It's kind of like this like two-way. We call it like a Z2 symmetry, but you know, you know, it flips and then it flips back, and you get back the original. So that's like kind of the generalized concept of what a mirror is. And it turns out that if you study like fundamental particle physics, there's like a lot of very, very similar attributes that arise in terms of like the properties of particles. Like people may have heard of like the fact that particles can have antiparticles, and the relationship between particles and antiparticles is very, very similar to the relationship between me and the image of me in the mirror. A lot of the same properties have, a lot in common. And so the idea of like mirrors in physics is actually has like a, very fabled long history. And so, yeah, there's a lot to unpack here, but I don't know. That's just an intro.
Yeah. And anything you want to add to that, Tim, before we delve into it?
Yeah, I think for the more mathematically inclined, we can take some analogies with just additions and subtraction, right? Like in elementary school, first you learn about numbers, right? One plus one is two, two plus one is three, and then at some point we learn about subtraction. Now you can do one minus one is zero. But what if you subtract a number larger than itself, right? One minus three. What does that equal to? We learn the concept of negative numbers, and in physics, a very similar situation arises, and we learned that in sort of in elementary math. We know that hey, if you just consider an extension of positive numbers, negative numbers, you can get like addition, subtraction, multiplication, division all for free. It just becomes an extension of the original self. And it turns out that in physics, this is actually very prevalent because, I mean, let's face it, physics uses math, right? And mathematically, the things that Mikey mentioned, particle, antiparticle, it's in a very similar vein, an extension of a particle. And it turns out that if you dig deeper into physics, there are actually many, there isn't just one way of mirror. It turns out there are multiple mirrors coming together and forming some kind of very intricate patterns. And I guess we'll dig deeper into that today.
Wait, no, like additionist attraction isn't the real like one of my friends actually a bunch of my friends were drunk once and they all like FaceTimed me and they were so confused about this concept. They were like, how come when you multiply something by -1, it turns negative, and then when you multiply it again by -1, it becomes positive again? And it's true, like they don't elucidate, like in your typical, middle school math class where you learn this, they don't really tell you why that is. But the reason why is exactly like the physics of it is like exactly a mirror. Like if you look at your reflection in the mirror, you get some kind of like opposition, something that becomes opposite. But then if you look at the mirror of the mirror, you get back the original. And, that is really the crux of, the content of like, negative number multiplication by negative numbers. It's absolutely like a mirror kind of symmetry.
Oh, that is interesting. So would that explain? So typically, when people hear about mirrors, they think about these spatial mirrors. Like when I look into a mirror, my left becomes right, right becomes left. But if I apply a mirror to that mirror, then again, it will map the left to right and right to left. So I'll get back to where I started. Is that the reason why you talked about particles to antiparticles? Because if I go from particle to antiparticle, and then I do the antiparticle of an antiparticle, it becomes the particle itself.
Exactly. It's exactly the analogy. Yeah.
Gotcha. That makes sense. So like what all kinds of things can we imagine like with this? So there's like the spatial thing of left to right, right to left. I'm assuming you can also do up, down, and down, up as well if you wanted to. And then also this charge and and particle and antiparticle type of transformation.
Well, up, down, and left, right, they're the same thing, right? Because it's just like depending on which way you're like oriented. Right? If I'm like this way, then up is right. The charge one is non-trivial, right? That's like a weird one. How do we?
Yeah, I think we can first kind of enumerate them. The first is the spatial one, right? Up, down, left, right, front, back. Doesn't matter where you place your mirror. Once you flip it, it's different. And of course, flipping up and down, left to right, it's just a matter of how you orient your mirror. So basically, they're linked together by rotation. That's how I put it. But we know that Einstein says that space and time are related, and they're all one and the same. But nevertheless, they're a little bit different. So there's reflection over spatial dimensions. There's also reflection over time. And it means going forward and going backward in time. And that, even though space and time are related, you actually can't, you can't just go from flipping time into flipping space. So those are different. So now we have two kinds of mirrors, mirror over time, mirror over space. And then, well, Mikey was mentioning something a little more abstract, particles and antiparticles, what gives? And this is kind of like, I guess in college, when you learn about complex numbers, you learn, for those of you who are familiar, or for those of you who are not familiar, when you learn about numbers, you have the real numbers, which goes from 0 to positive infinity. But then there's the flip side. You can go to 0 to negative infinity. The complex number kind of adds an extra dimension to that. It becomes two-dimensional now. So in this abstract way, for the particles, they can kind of move to the complex dimension. And you can link particles and antiparticles together. And those are just some of the, I think those are the main ones, right? There might be a few other more subtle ones, but for now, I think these three are the key ones.
Well, yeah, no, you can enumerate that there's, real, complex, quaternionic, and octonionic. Okay, let's just
yeah, actually, the three I mentioned is very critical in physics. They're called the parity, which is reflection of space. There's the time reversal, which is time forward versus backward, and the charge conjugation. These are called P, T, and C. And it plays a very critical role in physics, but we're not going to go too deep into that. But there's a reason why those three are the main pillars, but there could be others.
Yeah, the weird one, right, is that charge, like, for example, the charge of a particle seems to be like caught up with all of this, right? That's a weird one.
It's a little weird, but it works.
Yeah, it works. Yeah.
I like that explanation. It just works. I guess okay, so now kind of taking a step back, we've introduced these three different kinds of mirror transformations. Can we just give the audience a sense of like where this comes in, like what motivates this, and like why was this even considered? Like why are we even like talking about this kind of a thing? Why is this important?
It wasn't considered. It was almost like the discovery of antiparticles, like, I don't know, more or less happened by accident, right?
I wouldn't say totally accident. Like Dirac, we're trying to solve some equations. It's almost I think that there was a law. There's an equation that goes like something like x, something square will have to give you 0, but then that object itself cannot be 0. He was very confused. And at the end, the solution was, instead of thinking of those objects as numbers, they think of them as something that contains two parts. And it turns out that those are particles, a particle part and an antiparticle part. And somehow they cancel out to give you 0. This is a little technical, but that was Dirac's original.
No, but it was an accident because, like, if people didn't accidentally discover antiparticles, then there would be no need to explain any of this, right?
Of course, yeah. if they didn't discover antiparticles, they would be like, well, Dirac, you're wrong. So experimentally,
Dirac wouldn't even gone down this line of questioning, probably, right?
I think he devised his equations first, and then they discover antiparticles.
Really?
I think so. Yeah, he's a genius. Yeah.
I actually remember that too. His theory discovered antiparticles, like I think 50 years before they were discovered. Yeah, before they were seen. Yeah.
That's okay. My respect for Dirac has gone up even more than it was before. I didn't even think that was possible.
Yeah, he's one of my favorite physicists. But anyway, also won the Nobel Prize as well.
Did he?
Correct?
Oh yeah.
Yeah, he should. Yeah,
sure.
Yeah, he should have. But it's not always deserved. People who deserve it don't always get it.
Yeah. So I guess like kind of going back on track. What's like, I guess, why is this useful to consider symmetries from like a theoretical standpoint? Because like why should we even consider, like, if I hold a mirror to an electron, like what's the point of asking that question?
There's so many. Where do we start?
Well,
just lay it on me. Motivate this discussion.
I think first of all, it's a matter of mathematical completeness, right? Like, can you imagine studying, addition and subtraction, but then you're forbidden to talk about negative numbers? I mean, that would be so impossible. You'd just be like, well, 1 minus 3, impossible, just cannot calculate. That just doesn't make sense, because you could just calculate a negative number and carry on with your calculation. So part of that is just physics discovering the structure of particles, that what must exist in order for it to make sense. So there's a level of self-consistency. It's almost like discovering the structure of our world, right? Like if I have a left side, there should be a right side. If I have up, there should be down. So, and in the same vein, we have particle, we should have antiparticle. So part of that is surprising, and it's actually surprising that these things actually link to geometry as much as that. If there's a left, there should be a right. In the same reasoning, if there's a particle, there also should be an antiparticle. By that same logic, and it's not obvious, but then it can be proved kind of mathematically that, hey, just as much as left and right has to coexist, particle and antiparticle has to coexist.
Unless you're at 0, and then you are your own antiparticle.
Exactly.
Okay, so your argument is that, like, if a left exists, a right must also exist. I guess what else, Mike? You were mentioning there were like lots of other like motivations. Can you state another motivation of this?
Okay, this might okay, so I'm gonna start with like one that's like not great, but like I just want to point out that like okay, so like all of the atoms that make up our bodies, all of the particles that make up everything that we see here, we call these particles, and we call the other, the other stuff, we call those antiparticles, right? But that's a completely artificial distinction, right? Like if we were all made up of antiparticles, then we would be saying the same thing about particles, right? So like the physics between antiparticles and particles like are identical in terms of how they interact with each other. It's like literally like, you live in the negative side, you live in the positive side. Like it's almost like a asinine distinction. But then if you think about the idea of like balance, right? Like harmony and balance, right? Like everything should be balanced and harmonized. If we look at our universe, we don't see this. We see more particles than antiparticles, right?
Mhm.
Everything that makes up our existence is made up of what we call particles, and there are these like mysterious entities that can exist called antiparticles, but we don't see them a lot because when they hit a particle, they annihilate. But to me, at least, it kind of begs the question: like, does this exist somewhere? Is there like a mirror antiparticle universe somewhere? Like, maybe not here, but maybe it's spatially separated or another universe or something like that. So, like,
Mhm.
I don't know. Just yeah, it's not the best motivation, but it is a question you can ask, and it doesn't have to have a ridiculous
Yeah.
answer.
Yeah, and I would like to add that yeah, these are some deep theoretical question, and another one like Mikey was just going through. You can go to the three pillars of these mirrors: charge conjugation, parity, and time reversal. And Mikey just went through the charge conjugation. You can argue. The other one is time reversal. You can argue, well, even though the laws of physics pretty much looks the same for in time, backward in time, somehow our universe also seems like it's only going forward. And we have many episodes in the past, so I'm not going to repeat many of the arguments we made. But a question arises, though, is that would there be a universe out there that's kind of going backward in time to kind of have this balance, right? So these are kind of
Like
really
Benjamin Button.
kind of, but
Mhm.
but probably yeah. I guess it's all also like the movie Tenet, but don't want any spoilers. But yeah, these are intriguing questions, right? These are fundamental facts about our world. Our existence depend on the abundance of particles and the fact that time goes forward. But we don't really have a clear answer on exactly why that's the case.
Yeah.
Huh. So what I'm hearing is like these seem to be like, for lack of better words, I guess symmetries or representing symmetries. Is that fair to say?
Yeah, like these things, we know they exist. We know they can
Mhm.
exist.
Mhm.
And I don't know, maybe this is kind of a bias, but like usually physicists like to think that whatever nature can do, she will do. So these kind of like mirror counterpart versions of what we see should at least play some kind of role in determining the existence as we see it.
Huh. So I guess one question that comes to mind is like, if we held a mirror up to our universe, would it look exactly the same? Or would it behave exactly the same? Or would you be able to tell a difference?
That's interesting. So if we imagine that the laws of physics exactly respect this mirror, it should look
Hmm.
exactly the same. But we know for a fact that it doesn't. So that's the
Hmm.
conundrum here, because some of the laws of physics, when you look at the math, look at the equation, it's kind of like when you're trying to write down the laws of multiplication for positive numbers versus negative numbers, the rules are the same. Yeah.
Hmm.
But when you actually get to the calculator, somehow you realize that, well, shoot, like 3 plus 1 is 4, but negative 1 minus 3 is not negative 4. Something's amiss. That's what we're seeing. There's a contradiction almost, right? Our
Hmm.
universe is supposed to look the same, behind the mirror or in front of the mirror, but it's not true actually. If you change all the content of the universe to antiparticles, our universe actually would look quite a bit different. It's not exactly the same anymore. So that's a good question. It should, but it isn't.
I guess how does that show up? Because like I can drive my car like to the left or to the right, and the universe seems the same. So when you talk about like holding up a mirror to the universe in this question, what does that mean? And in the context of like, how do you know this isn't true? Without going too much into the details or like too nitty-gritty.
Wait, how do we know this isn't true? What do you mean by that?
I guess like how do we know that like if you hold a mirror up to the universe, you would think it'd be the same, but it's not actually going to be the same.
Yeah,
That means you'd
It
be able
would
to
be
tell
the
the
same, right? It's just
difference.
the definitions would change, right? It's like it's almost like a rewriting of the variables, right? Like
yeah,
it is
yeah.
the same.
Well, there are actually some subtleties. So it was discovered that what was that? That there was parity violation, for example. So if you look at some particles, a particle and an antiparticle, you might imagine the way they decay will behave very similarly, except all the decay product will be antiparticles. But it turns out that the direction at which particles get emitted, whether it aligns with the spin or not, differs for antiparticles. These are quite subtle and has to do with how a spinning top, if you look into a mirror, spins in the opposite direction, and there's this weird interplay between mirror and rotation and all that. But let's not go into details here. But the universe will have subtle differences in the way things decay, and also I think in some of the properties of fundamental particles. It's not
Wait,
exactly
sorry.
the same.
Let me ask I have a question. This is my own ignorance, but like, is that not just due to the fact that there is an asymmetry? Like, obviously, when we look at our universe, we see particles and not antiparticles, right?
Yeah.
So obviously, there is this asymmetry. Um, but will we still observe that if there was an actual symmetry between like antiparticles and particles?
I think we would, right? It's just imperfect.
Right. Wait, so then
Um,
how does that not explain the asymmetry then?
Sorry?
I thought the asymmetry between particles and antiparticles was the um,
Oh, I mean, it comes down to the details. The numbers don't match. If you calculate it, it has to do with phase transitions at the early universe. The amount of
no,
asymmetry
but
was not
phase
enough.
transitions they don't favor particle or antiparticle, right? If they did, then that would be an explanation for the asymmetry, right?
No, yeah. So I mean, this is getting into a little bit of weeds. Like we know
Yeah,
that's
sorry, I'm confused, so I gotta
yeah.
dig
We,
into
we,
this.
we, we know we know some of the mirrors are not perfect, right? We know that we can't just all convert to antiparticles and be everything is the same. It's not perfect, but that imperfection is very small. Yeah, and
But I thought that was a historical. I thought that I thought all those imperfections came from the fact that the universe is particle dominant and not antiparticle dominant.
um no. I mean, this imperfection could also washes out the asymmetry if you go to a phase transition. It's very technical. Like
Hmm.
when you go to electroweak phase transition, things could get washed out. So even if you start with an asymmetry, it can get destroyed. And it depends on whether something's in thermal equilibrium or not. But let's not get into weeds yet. I don't think
Okay, yeah.
yeah.
Okay, let's yeah. Sorry, I was
Like
confused myself, so I had to.
so these are slightly broken mirror. Let's put it that way. Like it's like looking in the mirror, but like it's a little off. But it's close enough, but a little off.
Yeah.
okay. So kind of taking a step back, what we're saying is that if you do hold up any one of these mirrors, to the universe, this time reversal mirror, this particle to antiparticle mirror, this spatial mirror of left to right, you can actually tell the difference which one you're in. Is that fair to say?
Yes.
No, but not if you hold all three mirrors, right?
Yeah. If
Like
you hold all
if
three
you
mirrors,
hold
yeah.
all three mirrors, then everything is perfectly the same.
At least we believe.
Mhm.
Yeah.
Yeah. If you only hold one of the mirrors, you'll see something weird. And if you only hold another mirror, you'll see something weird. And if you only hold two of the mirrors, you'll see something weird. But if you hold all three mirrors, then everything is the same.
Yeah. Okay, so if you so what you're saying is if you flip space, you change all particles to antiparticles, and you say that time is moving backwards, I would not be able to distinguish that universe from our current universe.
That's true, right?
It's only true microscopically. Unfortunately, the reversal of time is, again, if you go into the lab and measure it, yeah, you'll see that it's different. But if you follow the Big Bang, the fact that the universe gets bigger, it's not true. So, but
No,
anyway,
that's the CPT theorem. Has to be. We have not observed any violations of the CPT theorem. There's three mirrors. We call them C, P, and T. And if you use all three mirrors, everything has to be exactly the same. That's almost like a fundamental rule that we all.
yeah, but you can't flip time because the Big Bang happened. You can't in the lab actually do it.
Sure, cosmologically, yeah.
Yeah. So
But,
in
a box.
Yeah, in the lab you can test it out. In the lab you can test it out. But if you wait for the Big Bang to happen and to see where the universe right now, you'd be like, oh, oops, that didn't happen.
Yeah.
So what you're saying is even these three mirrors together are also broken even at a cosmological scale because you can't tell that time is going backwards by the universe getting smaller in this universe.
I wouldn't say it's broken. There's a different word for it. Okay, like in our universe, it's broken, sure. But if you look at the entire space of all the universes, it's not broken. Right. If that makes sense.
Oh, so you're referring to more of kind of a multiverse.
The multiverse theory.
Yeah, so I mean, Stephen Hawking in his paper proved that if you add quantum gravity in, it works. The CPT still works, but it means that quantum mechanically you need to have like different universes happening at the same time. But
then how are you not a proponent of the multiverse?
I don't think I was ever a proponent or opponent, for that matter.
No, but you were always skeptical of it. Is that not like?
Oh no! It depends on what you referring. There are many flavor of multiverse. Let's just leave it at that.
I don't know.
Let's leave it at that.
Convincing to me.
All right. So if you take into account multiple universes, then across all these universes, like this combination of things, you do the CPT, hold up these three mirrors. I would not be able to tell which, if I had applied that transformation. Am I understanding that correct?
Yes.
Just theoretically.
Yeah.
Okay.
At least we believe so. It's sacred. So.
Interesting. So, I mean, does that mean one of the universes is getting more compact than there's negative space or something like that? How do you I don't know, how do you just how does that work?
Yeah, there's universes with positive cosmological constants that are shrinking, and universes with negative cosmological constants that are growing. And I don't know, Tim, is that how this balances out?
Yeah, I think so. Because in quantum physics, all the possibility go at once, right? We're kind of just in that possibility. Of course, we can't see all the other possibility.
We're all just a mix of every possibility, and we just see one.
All right. So kind of I guess looking at this as a whole, I guess are there any other advantages to forming this type of framework of these three mirrors?
Yes.
I mean, yeah.
It solves paradoxes.
Yeah, I would say that maybe we're not giving mirrors enough credit yet. Like the listener, you might just be like, oh, what the heck? Why are we talking about mirrors? They seem so abstract, right? But if you consider string theory, which supposes that the way our universe is because of the shape of some really curled up dimensions, these mirrors that we were talking about will literally be mirrors of these shapes. Like imagine you have like a I don't know, hexagonal shape, then you can reflect it three different ways, right? So the way these curled up dimensions are, and the way they reflect, will literally create these patterns of particles, antiparticles, and so on and so forth. Right. So if we discover that these mirrors are exact, even if they're not exact, even if they're roughly approximately exact, it will tell us about the shape of the ultimate reality of our world. So it's very powerful.
Mirrors solve a lot of problems. It's just true.
I would agree with that in my own life.
No, I'm just saying, like, okay, so many problems in physics, like in particle physics and fundamental physics, have to do with, like, how do you deal with the fact that there are imbalances in things? And one of the generic solutions of dealing with imbalances is just assuming that, okay, it looks imbalanced here, but then when you really, really look down at the fundamental scales, it is balanced. And it's always some kind of mirror symmetry that's responsible for creating this balance. And that's why probably a lot of listeners are not attuned to this, but, like, people come up with all kinds of theories to explain the fundamental nature of reality, and so many of them contain mirrors, because mirrors are very useful for balancing, yin and yang. It's like, opposites cancel. Like, we live in a relatively peaceful universe that's not violently fluctuating its space-time fabric, and a lot of that could likely be attributed to the existence of these kinds of kind of mirror universes that could be living side by side with us.
Yeah, I think going back to Mikey's point, I think what Mikey was describing is exactly the situation for the forward in time, that the universe goes forward. One of the solutions is to say that, hey, look, our universe, sure, time goes forward, but if you look at the space of all possibility, then it balances out. And in the same way, like, hey, we have more matter than antimatter. Well, maybe if you look at all the possibilities, it balances out, but we happen to choose one of them. And now, a lot of these problems that are unsolved, for example, you can say, well, how come the cosmological constant is so small? Well, maybe there's a balance between positive cosmological constant, negative cosmological constant, which is the same thing as vacuum energy. Maybe if you look at all the possibility, they balance out. And in our universe, we're kind of slightly off. So those are, that's why mirrors are so helpful to explain, why things are so close to zero, or a tiny wee bit off zero, is this idea of balancing things.
Yes, -1 + 1 should be close to zero, and our universe is a peaceful, relatively peaceful place. There's got to be something going on there.
So Mikey, are you saying that zero does exist now, if there is balance?
No. Approximately, right? No. No.
Okay.
There's definitely no zero. Yeah.
Yeah, there aren't that many perfect mirrors. Perfect mirrors don't exactly exist. Usually, there's
no such thing as a perfect anything, but there's a lot of approximately perfect things, and we are existence to those things.
That's fair. We have an audience question. I guess commenting on more cosmologically about mirrors. Aren't black holes supposed to be open as white holes in anti-universe?
Well, yeah,
Any
time-reversed
comments
black
about
hole is
that?
a white hole. Yeah. So there might be, like Tim was mentioning, there might be universes with predominantly white holes instead of black holes.
Yeah,
I think that would be the time-reversed version.
I think for black hole is a little tricky because black hole has a singularity. So black hole ends in single.
No, there's no singularities.
Well, sure. Of course, singularity doesn't exist, but for our current understanding now, black holes end in this singularity, which is a characterization of unknown, right? But it's okay for black hole because black hole is a limited area, so everything ends in unknown, which is okay.
No, it's okay for black holes because the event horizon is a harbinger of a completely different description of the physics that's going on.
So we can.
Anything outside the black holes, we can't.
Yeah, the thing is, for black holes, it's okay to be a little ignorant. But for white hole, we cannot be ignorant because everything starts from the unknown because it's the inverse of a black hole. Things
Yeah.
come from the singularity. So if you don't know anything about the singularity, well, you're out of luck. Then you don't know how to do physics.
It's madness coming out.
Yeah. So that's why we don't know much about white holes theoretically. Yeah, and maybe that's related to why we haven't seen them, because if there's some theorem there's some conjecture that says the universe tried to shield itself away from these singularities.
No, we're not going to see white holes in our universe. There's
probably
no way
not. Probably not.
No, definitely not. 100% not. It's just a time reversal of a black hole is a white hole, right? And I mean, we've been learning a lot lately about what happens when information enters a black hole in terms of like how its information is, changes its encoding. So yeah, I don't know. It's not practical in terms of discussions for our universe, but I don't know. I would venture to say that as soon as we understand what happens at the event horizon of a black hole, which I think we're pretty close to right now, then I think we will have a pretty good description of what's happening with the white hole.
All right. Well, we'll have to see, Mikey. Yeah, so we're almost at time. So I want to give you guys a chance to leave the audience with any parting words, wisdom or anything from Mirror Universes.
Yeah, I would.
We did not get nearly as far as we wanted to with this, which is good. Which is good. That's good.
Yeah, there are actually so many more different mirrors that we didn't get the chance to talk about, which we could save for a later episode. But just this very naive observation in elementary school. Oh, they're positive numbers versus negative numbers, and then once we learn complex number, there's the imaginary number, real numbers, the negative numbers, the negative imaginary numbers,
the quaternions.
Yeah, and in the beginning, it all seems so abstract. But the moment you get to physics, it turns out that these lead to real consequences, these mathematical results. And it's interesting because remember what Mikey was saying, positive and negative is just a convention. Like you might think that we are the positive numbers. We could have been the negative numbers. Everything would be the same. And then the universe is this way. And it's kind of remarkable that there are these structures in our universe. There are these reflections, different ways of reflecting things. And there's still yet to be learned, I think. There's still a lot to be uncovered. We still don't have the full answers yet. But it tells us a little bit about what our universe really is like. So I think it's important to keep this in mind.
Yeah. The only thing I could add to that is that, people have been studying the possibility of mirror universes for a long time, and not just in one context, but in so many different contexts because there's so many different types of mirrors. It's kind of hard for me to believe that like a mirror doesn't exist on some level somewhere. And I don't know what this would harken back to, but just the idea of balance, right? Just the idea of like, I don't know, yin and yang, like for every, positive there's a negative. Like the universe doesn't respect that totally, but it has to respect that to some extent, I think, in order for things to work out as nicely as we see them. So I think this is like a very interesting just thing to think about, not like as an active research topic, because no one has any really good ideas. We haven't accessed enough, data to be able to make a statement on this, but just, as a theorist thinking about things, it's a great little playground.
Yeah, I found this discussion fascinating, and so on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all.
Bye-bye.